Oh, I think I zoned out. Welcome back, folks. Looks like it's time to start. So we're finishing off chapter 8, not in its entirety, but we went through some of the main applications that we were able to get to. If you look through chapter 8 and you decide there's just something in there that's interesting that you'd like to see brought to class, we could make that happen. So just let me know. But usually I think that the applications we took a look into are the main ones that folks want to see. And sorry, go ahead,
Did you
John.
just get eyes?
Oh, that must be there we go. And then once we go to chapter 9, really I view this as just being more applications of the integration process, but these applications go a little bit differently. We'll see how they go. There's an awful lot to say about differential equations. In fact, it intersects with linear algebra a ton if you're thinking about taking those courses. It's kind of interesting in a certain sense. But what we're trying to do is just give a really fast overview of what a differential equation is in section 9.1. We're going to go to section 9.3 and solve a class of differential equations called separable ones. Then we'll go to the section 9.5 to go for the first order linear differential equations, which is actually a humongous class of very, very applicable problems for the sciences, physics, biology, engineering, all that kind of stuff. So we're looking at just mainly an overview, not really the whole subject, which is pretty vast. After that, we'll be moving into chapter 11. So think of chapter 8, chapter 9. It's about together the concepts we are covering, about half the size of chapter 7, just a little break before we do the next chapters. Well, any questions at all, folks, before we jump back into 8.3? Okay, let's give it a try then. At full disclosure, we're working with a little bit of insomnia here. Well, me personally, a bunch of mandatory work meetings. So let me know if the numbers go sideways. When you get tired, that's when weird mistakes happen. But if we go a little bit slower, we'll definitely survive. So we want to find the centroid for the region bounded by these curves. This is red because I changed the function, but I don't think I recall to undo that. One way to start this one off is, again, imagine it's a real exam question. And this is how it might come into play. Let's put in y equals square root x. Next one would be y equals x squared. And there's an interesting algebra problem in here already. We need to find the intersection of 0, 0 and 1, 1. But for the graph I'd provide you in an actual exam setting, it'd probably look more just like this. And it would be almost implied. So let's change some domains and ranges. So that would be the graph that you would see. Probably both lines are black or something like that. And for this problem, it's also critical to know which function is the upper function and which function is the lower function. Color coding is not helping us out here at all. Anyone spot which is which? Good call. For me personally, when we say that, it just seems weird. We're usually thinking of root x to be a higher quantity than x squared, but not between 0 and 1. It's opposite. So good eye on that. This function here is y equals root x. This function here is y equals x squared. And I would provide that key on a real exam, because on the real exam, the concept is more just find the center of mass or centroid of this region. We can pretty much just read off the domain of integration from 0 to 1. And it wasn't even mentioned right here. So let's do a bit of algebra just to put that intuition to the test if it's really between 0 and 1. Algebraically, what you would do is grab both functions, root x, equate it to x squared. And algebraically, that kind of makes sense. If y is equal to root x and y is equal to x squared, set them both equal to each other, and we'll find the values of x for which they really match up. Over here, best way to solve this equation is to get rid of the square root. So square both sides. We'll get x on the left when we square it, x power 4 on the right. And now it's a polynomial equation we're solving, so we just collect 0 on one side. Those 0 is x power 4 minus x. Solving polynomial equations, usually your best tool is factoring. So go and take x, leaving behind x cubed minus 1. Then from here on out, the only way that's true is if x is 0 or x cubed minus 1 is 0, but we have immediate solutions now. X is 0 is already solved. There's not really any value in writing down that new line twice. And from over here, x has to be positive 1. Really, there's two more solutions, but this is the only real number solution. So x to 1. And that verifies we're really going between 0 and 1. I wrote this out all in orange just to say that if you were doing this as an exam problem and it felt to you it's obvious from 0 to 1, you can just work with that fact and that would be appropriate. But it's good to know how it goes down, just algebraically, in case you're ever in that situation, you really need to determine those bounds. Now, next step, we want the center of mass on this thing. First thing we need is actually the area. We want to know exactly what that area is. All I can tell you for sure is it's less than 1, taking 1 by 1. We know the area here is less than the unit square. So let's calculate it out as area is integrate from the bounds we see on the graph, or the bounds that we just found, 0 to 1. We want to find the area between. It does matter which function you put in, but if I got it backwards and put x squared in first, I have the opposite of the area, and you would know because you have a negative number. Take off that negative sign and it's suddenly the right area. But we want to do this carefully and not have to worry about weird mistakes and how to correct them. So to get the area, take the upper function. I'll write that in as x1/2. Subtract the lower function, x squared. And then now we're on our way with this. That's a pretty fast integral right here. We'll get antiderivative of x power 1/2 is x power 3/2 multiplied by 2/3 minus 1/3 x cubed. All evaluated from 0 to 1. Upper limit 1 gives us 2/3 minus 1/3. Lower limit of 0 gives us nothing. So now we're ready to go. Take away 1/3 from 2/3. And the exact area of this region is exactly 1/3. Now, if we had to guess the center of mass, I want to put it exactly right here. Because notice the weird oddity. There's less area here, more area there. The geometry of this shape is weird. So this is the red dot directly in the center. I bet you it moves a little bit more in this way, somewhere in that area, because of the extra leverage from this mass. So we have the area. Next step is to see if our x-coordinate is really less than 0.5, just slightly. So here we're doing x bar. Let's first write in the formula. X bar is reciprocal of area. Integrate from 0 to 1. If there was just one function here, you would go x times f of x. But if there's two functions, we go x times f of x minus g of x dx. Just like with the area, the order you put in the functions matters. But once you've got it once right here, just copy it down in the same corresponding way everywhere else, and you're in good shape. So that's just going to be f of x there for x power 1/2, x powered squared for g of x. And now we have reciprocal of 1/3, so that's just 3. Integrate from 0 to 1, x times x power 1/2 minus x squared dx. So this is where the problem really officially starts. Everything on the left is the formula. Now onto the right, we're doing 3 times a definite integral from 0 to 1. Distribute through when we get on this spot, x power 3/2 minus x cubed dx. Really no extra complexity as the original integral for area, just slightly different values here. So in the antiderivative, we'll take 3 times the result. By the red dot, new power is 5/2. So multiply by reciprocal 2/5 in front. Then go minus over here, a 4th x power 4. Evaluate this from 0 to 1. And we just about have the x coordinate. It's 3 times, throw a 1 inside here for 2/5. minus 1/4. And then you have to love the lower limit of 0. That just makes the work a little bit more streamlined. All of this is gone with 0 inputted. So that's the whole evaluation. And let's sort this through just to get a value, see how close it is. It's going to be, let's see, 8/20 minus 5/20. So 3 times 3/20, giving us 9/20. And if that was 10/20, it would be exactly at 1/2 for the x-coordinate. 9/20 moves it slightly to the left, so that actually looks like it's about right. Let's get an approximation as well. 9/20 is, well, it's not an approximation, exactly 0.45. Matches with our intuition. And notice there seems to be symmetry here, right? If the x-coordinate is 0.45, I would hazard the guess that the y-coordinate is 0.45 as well. But you are asserting, if you do that, that this line, y equals x, has perfect symmetry. These graphs can be confusing sometimes. With a slight change, symmetry is gone and we never see it. So even though it's plausible that y bar is 0.45 as well, let's show it just for the sake of practice and for carefulness as well. So here's step 3. Formula for y bar starts off the same, reciprocal of area. And then after that, it's different. Keep the same exact bounds, 0 to 1. In place of x, we put in a factor 1/2. And here, if there was just one function in the problem, we would take that one function and square it. This is the weird part of the formula. If there's 2 functions, you square the second function like this. But what we don't do is go this. Let's put in the warning or a caution. Do not use f of x minus g of x squared. That's a totally different function. It has 3 terms. This is highly specific from the derivation. It's the square of the first function, then the square of the second function. Kind of strange in a way. Oh, I actually want that arrow there. But at this point, it's the same idea as before. Drop in the functions in the same corresponding way. We'll have that y bar is equal to, that's kind of weird to put that there, right this way. Reciprocal of 1/3 is just 3. And before the integral sign, let's take out that 1/2, less of a distraction that way. Integrate from 0 to 1 of square root of x squared on the first term minus g of x, which was x squared, squared on the second term. So that's the format after inputting all the information in the formula right above. And this one is also not too bad. Let's work through this next. Any questions so far, folks, to this stage? Okay, working through it, we've got 3/2. Integrate 0 to 1. The function root x squared is just x minus x power 4 dx. And recall, we said the x-coordinate is 0.45. Somehow, some way, this is 0.45 as well. And if it's not, that means the symmetry we're seeing here was a lie. So let's see just how close we get. So next line, we'll do the antiderivative and get, let me drop it a line below, 3/2. From this term, we have a 1/2 x squared. So the next term is a 1/5 x power 5. Evaluate from 0 to 1, and it feels almost like deja vu. Just some fraction arithmetic, and we're on our way with this one. 3/2 times 1/2 minus 1/5 becomes 3/2 times, let's see here, let's go 5/10 on this one, minus 2/10 on this one, on the next fraction. So now it's 3/2 multiplying 3/10 which gives us 9/20. Exactly what we got up here. And that seems about right. It really looks symmetric, right? Based on the way it's plotted. This is a 1-to-1 scale and everything. But this confirms it to us exactly. It really was. Our conclusion is, therefore, center of mass or centroid, x bar, y bar, third way to call it, is at coordinates 0.45, 0.45, exactly. So whatever this thing is, if you build it and you need to balance it, here's the center of mass, right about there. Let's call it centroid, just a way to remind ourselves that's synonymous with center of mass. Well, that's the full process, folks. Any questions on that last problem here? Okay, well, when you go to do a problem like this on a second exam, notice how big it is. There's a lot going on here. You have to integrate 3 different times. You have to come up with the area, 1 coordinate and a second coordinate. So if this comes in as an exam problem, it's probably going to be not too complicated of a situation because there's really lots to do on these kinds of things. When you practice it in the homework, some of them are a little bit harder. Just keep in mind, I can't ask a long problem like some of the homework questions on a real exam. It's got to be all contained. But at this stage, we did it, folks. That's the end of what we'll cover in chapter 8. Let's clear this out, and we'll go off to the next exciting chapter, a very fast overview of differential equations. And I like the title of section 9.1. I don't often compliment the title of a section in a textbook, but this is really right on the money. What 9.1 is all about is really just mathematical modeling. That's where the differential equations really come from. We don't just write them randomly and solve them. The purpose of differential equations primarily is some context in the physical world. But before we get to the modeling part of this, here's the definition. It's not the prettiest definition. For analogy, think about defining a generic polynomial. When you define a generic polynomial, you say p of x equals a naught plus a1x plus a2x squared plus, and so on, an minus 1, xn minus 1 plus an xn. It's just a mess. That's how you define a arbitrary polynomial to a degree n, where n is arbitrary as well. And that's what's pretty much going on right here. We are defining an arbitrary nth order ordinary differential equation. Ordinary means our derivatives are, well, the ordinary ones. And in Calculus 3, you'll see new kinds of derivatives referred to as a partial derivative. So that's what splits the subject. The ordinary derivatives, the ones we're doing, Calc 1 and 2, and the partial derivatives you'll see in Calc 3. The nth order is just the order of the derivative that appears in the equation. So a differential equation is a function of an nth order derivative, a prior derivative, this is the n minus 1th order derivative, all the way down to the first derivative, kind of like when we define an n degree polynomial, we do the degree n term, the prior term, all the way down to the ax1 term, and that's what this is, the first order derivative. And then by analogy, the a naught here would be the function y, that's the unknown, and the function x. If we write out our differential equation just right, we can set it equal to 0. And so that means every differential equation can be expressed in that form. Not that we always express it in that form each and every time. It's just that you could if you wanted to. So f is a function of n plus 1 variables. And this one right here would be just an example of a first order differential equation. First order because it's just derivative 1. It's ordinary because we don't have any kind of partial derivatives being indicated. Well, that's just the definition. Any questions, folks, about this abstract version and the particular example below? Okay, now we're going to try out the modeling part of all this. Because again, this differential equation on its own, it's a mathematical curiosity. It's absolutely interesting. But if it's not tied to anything coming out of the physical world, there was not as much motivation to really study and solve this kind of a problem. This one, however, is very different. There is a ton of energy motivated in solving these kinds of equations. But first, when we say solving an equation, let's also mention one other thing. This is a very different kind of an equation, right? When you say equation, you're usually thinking maybe 5x plus 3 is 7, right? The solution is a number. But if you say differential equation, you're wrapping together functions, derivatives of other functions, a variable and the function itself, just some other function here as well. And the solution to this is a function y equals f of x. If we can find that function, we have a solution. Oftentimes, in contrast to this, there are infinitely many solutions. And so we're going for a family of functions that will solve this once and for all. So that's what's going on with the initial definition of differential equations. Deleting the polynomial definition just so it's not too much of a distraction. It was just meant to help us see what's going on with that up there. So that's what a differential equation is. And example one is us modeling with differential equations. So really fast one is populations. We're thinking about exponential growth if we're thinking populations. P of t is going to be the size of the population at time t. And then when we write this, dp dt, this is the rate of change of the population size with respect to time. So it's the rate at which the population grows or shrinks. Growth can involve negative growth as well, so we don't have to say or shrinks every single time. And now people who study this kind of problem really went through these kinds of thoughts when they put down the differential equation. We want to write down an equation that's going to capture this feature. It's reasonable to assume that the given population grows at a rate that is proportional to the size of the population. That's an experimentally verified fact for different populations over short time periods. Think a bacteria growing in a population, or excuse me, a bacteria growing in a petri dish matches this, where the population growth rate depends just on the size of the population until it grows for too long and it just runs out of resources in that petri dish. So modeling is imperfect. We're just modeling over short time frames. And over short time frames, we can write down a pretty good differential equation to capture this information. So that's what we're doing here. Write down a differential equation that models this population growth, and we'll use k for the proportionality constant, which is also called the growth rate or decay rate. So let's read this again. It's reasonable to assume that the given population grows at a rate. Right there is a humongous keyword. And it was said over here as well. Anytime rate or speed or anything that can imply a fraction with one unit in the top and another unit in the bottom ever comes up, we're probably talking about a derivative. So we said the population grows at a rate. So for this portion highlighted in yellow right here, they're literally saying verbatim dp dt, the rate of change of the population size, with respect to the only thing that's changing, time. So assume that the population grows at a rate. I don't have the equation, I just have one element of this sentence. This would be the equality, actually making it an equation. If you don't have equality anywhere, it's not a differential equation. There's no equation, in other words. So it grows at a rate that is proportional to the size of the population. Well, when you say something is proportional to something else, you grab a proportionality constant, k, and you multiply it against whatever it's proportional to, k times p. So this equation right here, if we read it out left to right, says rate of change of the population size with respect to time is k times p. But k times p in this context is just another way of saying proportional to p. Well, we got it, folks. That's our differential equation for population growth. In Calculus 1, this is studied a good a bit, depending on if the Calculus 1 instructor went into that section on exponential growth and decay. But what we really don't have opportunity to do in Calculus 1 is actually solve this thing. That's what we want to do right here, right now. Let's solve that differential equation. Calling it a differential equation right now is appropriate, even though dp dt is a derivative. That means if we were to write down the formula for dp dt, we would write dp dt is limit h goes to 0, p of t plus h minus p of t divided by h. So that's just the definition of the derivative anytime dp dt comes up. Well, the limit definition. So if we're going to solve this, that's actually not what we want to work with. We want a literal differential. It makes sense, right? If we're in differential equations, we want the differential to help assist us in solving the differential equation. And so here's what we do next. Down below, dp dt equals kp. We're going to completely change our perspective. And over here, view as a differential. So what does that mean? If the right-hand side is a differentiable, then dp is one symbol on its own, dt is a different discrete symbol on its own. It's not like this where dp dt are just essentially attached together. We could split this up and just write out dp is equal to k times p dt. So this is what the differential would look like. And in fact, it's just the differential of saying, taking this. Let me backtrack on that comment. I was thinking of y equals p of t, but that'd be some conflict with the variables down here. But I think this is a better analogy. View this as a differential, split it up, and now this is an application of integration. Integration is going to help us here if we arrange things just right. For example, I don't want to integrate the left and the right at this stage, because if I attempt to integrate the right-hand side, I have a mismatch on variables. P should go to the left of dp, so that if I integrate something involving dp, it should only involve variable p itself. So next step is to separate out variables. Let's say it on this line. Separate variables, and that's going to give us, keep dp right where it is, equals, divide out p on both sides, so 1 over p on the left, equals, give it some space before writing k on the right, and dt. Recall, k is just a constant, the constant proportionality. So if you put an integral on here, there's no trouble. That's just going to be k times t. But if you integrate one side of the equation, you are forced into integrating the other side. So here's what it would look like. But we're just about there. Well, not really, but we're making progress through this. And in solving this differential equation, notice there's already kind of a bit of a trouble right there. If I've got 1 over p, there is one situation where this is not going to be great for us. P of t denotes a population size, so it'd be okay if we said P of t has to be strictly greater than or equal to 0, or strictly, I should just say greater than or equal to 0, not strictly at all. That's a reasonable assumption to make. But what about p equals 0? That would mean that there is no population, it got wiped out. But that should fit into here. If the population is just dead, we should be able to describe the growth rate as well. It would be 0, right? For everyone wiped out in the population. So P of t is implied to be greater than or equal to 0, but it can't be 0 right there. Nonetheless, P equals 0 still could be a solution to the ordinary differential equation at the very top. So let's say this as well. If P is 0, then the derivative of P with respect to t is 0. I guess that makes sense, right? The derivative of any constant is zero. So the left-hand side would be zero. And k times p, we're looking into the right-hand side next, would be zero as well. This verifies to us y equals zero. Excuse me, not y, rather p equals zero is a particular solution. So it is a solution to the original differential equation right here, but it's like a fringe case, right? It's the weird case that does in fact fit here, but almost all of the other times we're considering p strictly bigger than zero, no potential for equality. That means what we did here is allowed. We have the particular solution to the right. So on the left, we'll just assert p is not equal to zero. There's an actual population size there, and now this makes sense in the denominator. Which means we can just integrate it, right? It's going to be the natural log, absolute value of p. We put in absolute values because that's just our process. We don't want to forget to do that. But we're asserting the population is non-negative, so we can drop it on the next step if we like. On the right-hand side, it's a constant k, but if we're integrating with respect to t, we multiply it by t. And this step is vital. We can't put it in on the very last step. We have to put it in right here, right now, or else the algebraic form of our solution could be very badly damaged if we try to put in a constant at the end. So we must include plus c right at this step. Really no getting out of the way with it. Sometimes you could add it at the final step, but we will see plenty of examples where you didn't do it right at the step you complete the integral, did some algebra here, you're not going to get the right form of the differential equation. But we're almost there, folks. Our goal is to solve this differential equation, the one above, which means we're going for a function, p of t equals something. And we can do that. You just take a base e exponential on the left to the power of natural log absolute value p, base e exponential on the right to the power kt plus c. And this effectively says equation above is true if and only the equation below is true, because if the bases are the same, then the exponents have to be the same, is essentially the logic here. But now we've got a good cancellation. That's gone. Let's include the statement p strictly greater than zero so that we can write just p without absolute values. Back over here, p could be rewritten as properties of exponents, e power c times e power kt. And then finally, this is taking more space than I thought it would. Let's make one last step. That e to the power c, it is correct. This refers to any non-negative number whatsoever. It doesn't even include zero. It is interesting because if this can't be negative, it's a little bit restrictive on the solution up here. It turns out a negative constant in front still solves the original differential equation. But if we're thinking about mathematical modeling, so we were worried about the context of population size, it's okay this time to solve it and just assert non-negative integer there. So here's our final solution, or our final line. P of t. Notice this time we're using function notation because we want to emphasize here's the function now. Whereas above it was just p because we're thinking of it as a variable. So we could symbolically work through the solution. P of t is going to be equal to, I'll call it C1, e to the power kt, where C1 is equal to, let's say it this way, C1 is bigger than or equal to zero. So what I've done here is I've taken this. That's strictly bigger than zero. It can't actually ever be zero. But we're rolling together that as a particular solution by allowing the constant be equal to zero. It allows P of t itself to be the zero particular solution. So we took something that's strictly positive, included the possibility it could equal zero, threw it back in, and just called it a new constant. Some people might call it just C, And that's not too much of a harm. But the people who teach differential equations at our university and the others are opinionated people. There's lots of schools of thought, and some people say when you include a constant here, but make a change on that constant, you have to track it and say what is C1 and mention the new constant here. So we're going with that format there. But again, if you just put in C, that would have been all right as well. Well, we did it, folks. Our claim here altogether is that, let's go all the way to the top, if the population grows at a rate that's proportional to its size, then the formula for the population is that, because it was a solution to the underlying differential equation right up here. So we found a solution. Any questions at all, folks, on that process? Okay, but now think, what do you do in ordinary algebra? In ordinary algebra, if you have found a solution and you were learning this for the very first time, maybe in elementary, for example, the next concept is immediately verify that it is a solution, check your work. If we don't have a good handle on how to check if a solution is a bona fide solution, we're still missing something in what we did right here. So example one is just a big introduction to differential equations, really. We modeled in part A, we found a solution to the equation in part B, and part C, we're not done until we can show how do we check that really solves this up above. So that's going to be our next thing to do. Let's take this right here, underlying differential equation, and check that this solves it. So how would we do that? Well, notice that there's a derivative on one hand, the function times k on the other side. So we should just take our original equation here, take p of t equals c1 e to the kt, and differentiate. Only reason we're differentiating this is because it's a first order differential equation. Only the first derivative comes up. So that's really all we need to verify. So come down right here, immediately differentiate it. You could write a p prime if you'd like, but it's a good call to call it dp dt just for the sake of matching up the Leibniz notation over here. Not a requirement. P prime does just fine as well. If we're differentiating dp dt, it means we're differentiating this. And C1 is a constant. So if you could go C1 times ddt e to the kt, well, that's a fine way to start off this problem. Constant multiple rule. Over here, different rule. This one's a chain rule. We'll get C1, derivative of a base e exponential function is itself, to the power kt, the inner function. But because it's a chain rule, we multiply by the derivative d dt of that inner function, kt. K is a constant, so the derivative of this is just k. So this becomes, here's the k for where the red dot is, times c1 e to the kt. If we color code this p right here in blue, c1 e to the kt, that's p right here as well. K also occurred, k. So we have a conclusion, therefore, dp dt equals, make some substitutions. This one's just a copy, but c1 e to the kt we'll write in as p. The input of t suppressed in the differential equation, but it's emphasized here when we're just indicating it as a function. So we did it, folks. This shows p of t is a solution because this is a function that satisfies the original differential equation. When we go to differentiate, this long chain of equalities got to the right-hand side, in other words. Well, any last questions, folks, on running through this introductory example? So that's essentially what differential equations are all about. We'll solve a lot of interesting ones in sections 9.3, 9.5, and pair them with applications at the end just to show the tie-ins to the physical sciences. But for what we'll do next in these notes is focus a little bit more on part C. It's actually kind of tricky to determine whether you really have a solution to a differential equation, depending on the actual format of the differential equation itself. This one wasn't bad because it just said derivative equals this expression. So we just had to take the derivative and showed we can mangle it some way somehow and force in the right-hand side. But this next differential equation is different. It says determine whether the given function, that's y, is a solution to the differential equation, that's y prime plus y equals 2 sine x. This one's first order as well. So the steps look a little bit different this time. Take your y and just immediately differentiate it. Y prime. Derivative of sine is going to be cosine x. Derivative of cosine x is negative sine x. So we have cosine plus sine x. So there's our y prime function. You can put that right inside there. And because this is first order linear, actually that's the only derivative we had to take. But the algebra looks different this time, right? The differential equation has a little bit more going on the left-hand side. We have the derivative of the function and the function on the left-hand side. So now, once we get the derivative, next step, let's call this step 1. Step 2 is to verify if our given function and the derivative satisfies the differential equation. So begin by copying the method above. So let's start with the left-hand side, y prime plus y. Equals, but don't put 2 sine x in. We just want to throw in what we found, simplify it as much as possible. And if we can show that we landed on 2 sine x, our work is done. If there is any difference whatsoever that you spot, like 1.999 sine x, it's not a solution. So here, just make some substitutions. That's most of mathematics, it feels like. For y prime, put in cosine x plus sine x. Add to that the substitution for the original function y, given at the top. Sine x minus cosine x. And at this stage, would you all say it is a solution or is not a solution? A lot of people shaking their heads yay for yes, it is a solution. I agree with you. We still need to take one more algebraic step, but we can kind of see it now. We have cosine canceling off. Thank goodness, because there should only be sine on the right-hand side. And these two are like terms. We have 2 sine x. Matches up with the right-hand side. But on these problems, our work is not done. There's a 1-point thing that we still have to say. And it's silly, I know, but it's actually really important to say the last thing. We have to clearly state our conclusion, because the whole purpose of this is to determine if y is a solution or not. I need to know that you know what the overall conclusion is. So don't forget this third step. Conclude. We said, well, we matched up the right-hand side to sine x, so y equals sine x minus cosine x is a solution. We don't necessarily want to say the solution on these kinds of things, because for a differential equation like this, there's often infinitely many different solutions. So we either say a solution. Up here, we said, well, we didn't say anything, but we have a solution. Notice it's infinitely many solutions altogether, really, because of the constant of integration right here. So that's pretty much what we're doing so far on these notes. If you introduce differential equations, really the major key concept is, how do you know when you have a solution? For foggy on that, differential equations is always just going to look like a mad science. So we should practice this again. Here's our part B on this. On part B, we have quite a bit different function and a quite a bit different differential equation. Now it's the product with y by y prime minus x. But it's going to start off the same way as before. We will plug in a function y. We already have it. It's right here. We need to plug in a function y prime, and then just check the whole left-hand side, when substituted in with the right information, balances to 0 this time. That means really the first thing to do is differentiate this. So let's write it in as y prime equals a square root, like we mentioned before, takes this entire root structure, drops it into the denominator with times 2. But because it's also a chain rule, we go times the derivative of the inner function, which is the 1 minus x squared, going in both of those placeholder symbols we left over. Then it's a fast derivative. This is in the numerator, 2x. So our 2's are going to cancel. And altogether, it's just x over root 1 minus x squared. Oh, good call. I'm not too sure what I did with that negative sign. Thanks for spotting that one, which means negative x here as well. And that's all it takes to make something that could have been a solution a non-solution, or vice versa. Well, with that in, last thing to do is just drop all this information into the equation. So let me write in, just as a paper trail, we're taking y by y prime minus x. So that'll be equal to, first take y, root 1 minus x squared. Multiply against y prime. So that's going to be the negative x, root 1 minus x squared. And then just minus x from this part right here. How does it look to folks so far? Does it look like a solution or a non-solution visually? A little bit harder to see this time. And if it's harder to see, probably not a solution. Yeah, absolutely. It had to bounce to 0, but thanks to the fix on finding that negative sign, it won't. If we forgot the negative sign, it would have, and we would have made a mistake on that. So these cancel. All that's left over is going to be equals to negative 2x. Once we get to the simplified expression, we come back over here. It was supposed to be equal to 0 if it was a solution. And we'll say this time, not equal 0. So the last thing is our conclusion. Let's say, therefore, y equals root 1 minus x squared is not, let's emphasize it, not a solution. So it being a solution just means we have equality here when we made the substitutions. Non-solution means no equality whatsoever. It was so close as well, but again, that one negative sign is all it takes to throw it all off. Well, any questions at all, folks, on verifying solutions at the moment? Okay, it's kind of a weird process so far on these notes because with any one of these examples, we haven't showed the process of finding a solution whatsoever. We only did it on the one problem. But again, think of section 9.1 as starting off kind of slowly as an introductory topic. Next thing we'll do is same thing as we did before, but verifying if you have a solution just feels like a strange mathematical oddity unless you could attach context to it. So here's one with context. Same instructions as before, but this time we're talking about hanging a cable between two poles. This is a famous problem that involves hyperbolic functions. The curve when you hang a pole between two cables is a curve that sags a little because of the weight of the cable itself. That curve is called, I believe, a catenary curve. And hyperbolics, let's go over here for just a moment, are the famous curves that solve this problem of how do you model a hanging cable or a chain or those kinds of things. And it's useful for other things as well. For hyperbolic functions, this document right here is just a quick overview of different concepts. I think it's cool to know that if you're doing trigonometric functions, your geometry is on the unit circle, x squared plus y squared equals 1. If you change that just a little bit, put in a negative sign, your equation is now a hyperbola, and, well, this implies a new identity. There's an area argument as well. For trigonometric functions, a denotes the area of the sector, then t equals 2a. So you can tie this together with areas. And this area right here, this takes loads of calculus to show and derive. But just as before, we have a coordinate here for cos t sine t, just like a coordinate for cosine t sine t. Same area argument, area is twice a, t equals twice a coming from here. And we've defined hyperbolic functions. Here's the really weird thing about all of this. Trig functions are the weird ones, and we'll see why in chapter 11. The hyperbolics takes lots of work to derive this, but you can never do this for a sine function. If you want to write down an equation for a sine function, you divert to draw the unit circle and rotate to the right amount and take this second coordinate. That's defining a function in like the worst possible way, right? It's a whole process on the geometry of a different curve. So is this one, but you can actually define hyperbolic sine using finitely many arithmetic operations. That's impossible for ordinary sine. You need infinitely many operations, really strange out of nowhere. So those are the hyperbolics. If you were to graph them, they look like this. Finally, these are the derivatives. And just like there's trigonometric identities, there's hyperbolic identities. This one right here is the weird one because we usually say cosine squared plus sine squared is equals 1. This time it's a minus, and it's only because the geometry had a minus right here. That's the only thing that directed that identity. So there's our overview of hyperbolic functions. Before we get started, let's scroll to here to recall taking the derivatives. This is here for completeness. I don't think these have ever come up in a Calculus 2 course. You would have to work at that for this to come up. But now, back to our problem right here, we can verify this differential equation using that knowledge of the hyperbolics. It says for the write-up, using principles from physics, we'll have to ask our local physician, Kristen Barnaby, on how this works. It can be shown that when a cable is hung between two poles, it takes the shape of a curve, y equals f of x, satisfying that differential equation. So this one's different this time. This is a second order differential equation, which is very often paraphrased as diffie-q for differential equation. It's second order because the second order derivative occurred on this one. So rho is the linear density of the cable, g is the acceleration due to gravity, t is the tension on the cable, so all those physical things are just constants. It says next, t is the tension on the cable at its lowest point, where it's sagging the most. That's interesting. Here's the vague thing we might have to ask our physicists to clarify for us. And the coordinate system is chosen appropriately. Our author doesn't give us any information on that. He's just essentially saying, trust me, this is the right equation, and that's the solution to it. So when it says the shape of the curve from a cable hung between two poles is y equals f of x, that's the y equals f of x right there. Actually, let me double check my color coding. Function is green. Let's not change that right here. That'd be a bad call. So there's the function in green. And here's the second order derivative here in blue. And here's the first order derivative here in yellow, running out of colors on this. If we can put this all together, we'll be able to verify if it really satisfies the equation up here. Well, let's give this a try. If it's a second order differential equation, you are guaranteed doing two derivatives this time because the second order derivative occurs. So step one is just to differentiate this once. So let's pause right here for a quick review. Notice when you differentiate hyperbolic sine, hyperbolic cosine, we just flip from one function to the other and no negatives ever occur. That's kind of convenient in a way. So first order derivative is going to be dy dx. Highlight that in yellow just to convey the color coding up here. So dy dx is going to be equal to, first, t, rho, and g is just one big constant. All of them are constants, so go t, rho, g. Then differentiate hyperbolic cosine, turns into hyperbolic sine, so sine h. That's an absolute chain rule process because the function inside is not just x. So we'll go like this to visualize it. Write in rho g tx on this one, rho g tx on that one, and we're on our way for the derivative. And the derivative here, this is just going to turn into rho gt, canceling with that, t rho g. So t over rho and g, hyperbolic sine rho g xt, I'll write it sideways there to save some vertical space, maintaining that notation, times rho gt. Here we have a huge cancellation of all the constants, and it's just that hyperbolic sign of rho g. Now I've ran out of horizontal space, so I'll go in the more vertical notation here. We did it, folks, that's step one. And now, because it's second order differential, we do it again. Differentiate this one more time. It's easier the second time. It's kind of curious because now it's just a chain rule. Let's go d2y indicates the second order derivative. dx2 indicates we're differentiating with respect to the variable x both times. And we get cosh rho gtx multiplied by the derivative of rho gtx, which is just another rho gt. I want to put that constant in front, so let me copy it one more line. So we've got all of our derivatives. All we need to now do is put everything together right here. This time, we're just going to drop down that whole equation, do two substitutions here and here, and see if both sides balance. So here's how it looks. d2y dx2 equals rho gt root 1 plus dy dx squared. And maybe, by the way, a really interesting side comment. This is about a cable being hung between two poles. It sags. But notice this is an interesting feature because that's part of the integrand when we define the length of a curve, like a cable itself. It's kind of interesting that it must have worked its way into the derivation some way, somehow. But now here's our original differential equation. We're now making two substitutions. Two substitutions. Y never even occurs in this one. So on the left right here, drop in what we had from step 2. Rho gt cosh rho gt x. On the right hand side, we're copying in until we get to the yellow. Rho gt root 1 plus. Here's our last substitution. This whole thing just drops right in. Sine h rho gt x squared. Okay, so well, we did it, folks. Those are our substitutions. I'm happy that that matched up. That's nice, right? But what about everything else? Doesn't look good, right? This looks actually pretty bad. Except, just like other trigonometric identities, there is a full set of hyperbolic identities. Every single thing you did in a trig class can just be redone with the hyperbolic functions, every little bit. It's kind of weird. So if we go back to our cheat sheet here, let's take a look into the hyperbolic identities. This one right here is the most fundamental one because it came from the geometry of the hyperbola itself. Steal this one. Let's drop it in right here just for a reference. It's not quite the exact identity we even want, right? But one identity like this implies three other ones. An associated identity to this one is that cosh squared x is 1 plus sinh squared x. The x is actually rho gt, but that just means this whole thing inside here becomes cosh squared rho gt. So let's do that on our next line. On the left, rho g over t cosh rho g over tx, takes a while to actually say these, equals rho g over t root, inside here, through the identity, it's cosh squared of rho gt x. And this is also cause for concern because we always have to constantly think about this. The square root of a for anything squared is automatically the absolute value of a, and we need some justifications on dropping the absolute value here. If I can't drop that absolute value, we haven't verified this as a solution. So one other thing to check. Back to the hyperbolic functions. Again, this is a massive crash course on it. But here's where the plots come into play. The derivative of hyperbolic cosine is the solid line, and these are just values that it's going to approach. Interesting equations, right? It's part of the definition of cosh. But this tells us hyperbolic cosine is just strictly positive, so that when we go to take the root, there is no absolute values whatsoever. So let's throw this in as well as a justification of our final step. So last thing we can say for our conclusion, I'll leave these things on just the next page, just as a reference. That part right there is just cosh rho gt. So we have rho gt cosh rho gt x equals rho gt hyperbolic cosines of rho gt x, and that's a perfectly balanced equation. So back up here on the top, we can say, therefore, don't forget the conclusion, y equals t divided by rho g cosh rho g over tx is a solution. Kind of a lot of work on this one, but again, the problem with a real application to the physical world like this one is that it's just automatically going to be a messy problem based on the ones we were just looking at. But it's an honest problem. This is a honest to goodness differential equation, and these are the steps on how you would verify it as true. We just needed a whole bunch of additional facts down below. So this one wouldn't make a good exam question, but definitely a good one for looking into solving these kinds of equations. Any questions or comments whatsoever, folks, on that full process? Okay, well, there's just a couple more concepts that we would want to talk about before we close out this section, and that's equilibrium solutions and solutions where the solution to the differential equation would be increasing. We want to know solutions for which v, the solution to that differential equation, is decreasing, and that could give us a lot of intuition about what's going on with this differential equation here. We are going to reuse from Calculus 1 the increasing decreasing test, which makes a lot of sense because f prime being bigger than, let me say that again, f prime being greater than 0 is just the same as saying dv dt is greater than 0. So this applies to differential equations as long as it's a first order differential equation. And it's a kind of interesting problem because this describes how our brains work, the electrical impulses between neurons. So if we can understand that differential equation, we have, well, a deeper insight into neurology. But always remind yourself that it's just a model. It's not perfectly how anything works. It's just the best thing we have over, well, with what's been worked on or derived so far. Definitely we can't do this in 3 minutes. So we'll come back on Thursday's class and finish this one off and then move over to 9.3. Well, have a great night, folks. If you have any other questions, I'll be happy to help out. Right, I don't think we would want to try to write as fast as possible on this one. But have a great night. If you have questions, I'll be happy to help out.
Yeah, I got way worse. Good one. Yeah. I love to do it. I love to look at that.
Relating to Monday's lesson, on the exam, are we gonna be required to make the graph of the equations that we're working with? Or is it kind of just like a check?
Oh, so for the real exam, I would actually provide the graph. It's going to be printed right on.
Okay, so we can kind of use that to gauge it.
Yeah, exactly. That's going to be the major purpose.
Okay.
So yeah, those will all be provided.
Thank
For the
you.
homework though, it's up to us if we want to do those or not. Yeah.
Thank you.
Yep, absolutely. Yep, you too. Take care.